This video is on Newton's method. Newton's method is another approximation method. So just like linearization was in the last video, Newton's method gives us approximations of things. Linearization was really good for approximating values around a certain point. Newton's method uses those linearizations to try and find zeros of functions that it's hard to find a zero with. For the warm up, find the zero for this. Hopefully you did that already, but that basically means you substitute 0 in for y, and then we're going to find this. So 0 minus y naught equals f prime of x naught times x minus x naught. We get negative y naught divided by f prime of x naught equals x minus x naught. And that comes from just realizing that 0 is in front of that. That doesn't mean anything. Then we divide by the derivative. Then our final answer is going to be when we add x naught over, we get x equals x naught minus y naught divided by f prime of x naught. What's important to understand for us is that y naught is equivalent to f of x naught. So what we're going to do, this is actually Newton's method. We repeatedly do this over and over again to successive iterations of x naught. So we get x equals x naught minus f of x naught divided by f prime of x naught. So here's the procedure for Newton's method. Make an initial guess, find the equation of the tangent at this point, and find its zero. Do that over and over again until you get as close as you are required to or you are desiring to get. So if you need to continue writing that, press pause in the video. One thing that we want to talk about is like what's actually happening. So let's take a look at this picture. If we want to find the zero on the left side. So in this problem, negative 1/4 x squared plus 2x plus 6. If we want to find the zero on the left side, we just have to make sure that our guess is closer to the zero on the left side than it is on the right side. If not, we'll get the wrong zero. So for example, if I guessed a point over here, I will end up approximating the zero that is between 10 and 11. But if I want to approximate the zero that's between -2 and -3, I just have to pick some point that's closer to that on the function, and then get its linearization. What's going to end up happening is after I get that value, I'm going to take, it looks like it's a little bit to the left of -6. I'm going to take that value on the function and do another linearization and find that x naught minus f of x naught divided by f prime of x naught. That gets me another linearization, and then that gets me a little closer to the zero. The third iteration gets me even closer to the zero. So as we move closer and closer, do more iterations, we end up getting closer to the zero. If I picked a point that's closer to the zero to start, then obviously I would get closer at sooner iterations. So my second iteration might be close enough for my liking if I got close enough. Um, Now, one more thing that you have to notice is that it might take a very long time if you make a very bad guess. So if you get it closer to the vertex in this problem, we don't even know where the second and third iterations are unless I zoom out very, very far. Um, Again, notice that if I'm on the right side, I'm going to get closer to the zero over there. Okay, so that's just kind of what's actually happening when we're doing this. Finding a root for f of x equals 1/2 x squared minus 3, y minus y star. Now the reason we're putting that star in is um, as you continue to go on in successive iterations, it might be y1 and x1, y2 and x2. So as we move forward, we kind of keep going on. The way that I like teaching this is in a table. Um, So I just like doing the table because it's easier to remember. Now, you could take this equation and solve it for x every time, and then that gets you your next x value. Remember that we're always making y equal to 0 because we're trying to approximate where this ends up equaling 0 here. So we want to get a 0. Um, but I don't really feel like that is the best use of our time. So I like to make a table. So we put iteration number. Um, so my first attempt, I'm going to have x. Let's just say I guess 2. Okay, so if x is 2, that gets me here. So I'm going to want to try and get something that's relatively close to a 0. And if I plug in 2, f of x is -1. I don't know why it's dotting here. F prime of x is also 2. So then this last spot is x minus f of x over f prime of x. Remember, that's what happened when we solved that equation at the beginning. That was our warm up. So I'm going to take 2 minus -1/2, or 2 plus 1/2, which is 5 halves, or 2.5. So my next thing, okay, so my next spot, I'm going to use whatever I had for x. I'm going to put that here. So that's 5 halves. So what's happening on the graph is I took the tangent line, it ends up intersecting at 2.5. And so then I'm going to take whatever the value of the function is at 2.5 and then make another linearization. So that's kind of what I'm doing right now. So I'm making another linearization here. So if I put 5 halves into the equation, f of x is 1/8. If I take it into the derivative, I get 5 halves. By the way, if you didn't take the derivative yet, you probably should have. You get f prime of x equals x. So what ends up happening is if I take it into x minus f of x over f prime of x, I get 5 halves minus 1/8 over 5 halves. If I simplify that, I get 49/20. So that becomes, in iteration 2, what I put in for x. So I just continue to take whatever this value is and put it into the next iteration. You're often told to do this for a certain amount of iterations. So if it says do 2 iterations of this, you would be done right here. So at the second iteration, I am now done. The first iteration gives me 5 halves. The second iteration gives me 49/20. So oftentimes they will tell you do this for 2 iterations, do this for 3 iterations, or they will tell you to get it within um, a certain amount of values, get it within zero point 0.1 or zero point zero 0.01 of an actual 0. So let's look at what this looks like on Desmos and what actually happened. So um, if I take this chart, I kind of just took the chart that I made and then I put it on Desmos, because what ends up happening is once you get that 49/20 or 2.45, then the numbers get really nasty. But notice what happens after you do the third iteration. You get 2.4494898. It gets really close to what the actual 0 is very quickly. Root 6 is actually the 0, and plus or minus root 6 clearly. So if we picked a point that was over on the left side of the vertex, then we would have got -2.4494 and so on. But notice how this value on the table is within a very, very small amount of the actual root. Uh, so if I quickly can change what happened here to show you the actual tangent lines that are happening, I will do that. So 1/2 x squared um, minus 3. And if I make x naught equal to 2, this is actually what was happening with our first, second, and third iterations. We got these particular points. So we got 5 halves, and we got um, the second one you actually can't see right now. So the second one was 2.45, and then the third one, which we didn't do, would be even closer. So that's what actually happened in our graph. Last thing, use Newton's method to find where y equals x cubed minus x crosses y equals 1 using x equals 1 as the initial guess. Um, so I'm glad that they're telling us to use x equals 1. I tried x equals 2, and trust me, it's a lot worse. It doesn't mean that it gets there any slower. It just means it's a lot harder to do by hand because when you plug in 2, it gets really nasty really fast. Um, there are two things that I need to make sure that you're aware of. When it says that your initial guess is within 0.0001, that means that the actual value for y minus your final estimate has to be less than 0.0001. Okay, so your actual minus the estimate has to be less than 0.0001. Since that's going to be very hard for you to do, finding the actual value, especially if it's a no calculator question and you have something like this, what you're going to have to do is that means your second to last iteration subtracted from your last iteration has to be less than 0.0001. So that is how you can tell, because your second to last thing in Newton's method subtracted from your last thing in Newton's method has to be less than 0.0001. Finally, in this problem, if you're being told that you have to find out where it crosses y equals 1, that means that you have to replace y with 1, not 0. So you're really doing a, a vertical shift of this, and your new function, you either do 1 equals x cubed minus x and subtract the 1 over and set that equal to 0. But really what that means is your graph is going to look like the graph of y equals x cubed minus x minus 1. You're technically getting a new function. So this 0 that we're trying to find, well, this 1, quote unquote, that we're trying to find becomes a 0 if you do the vertical shift. I want you to try Newton's method for this, and then we will talk about it. Okay, so hopefully you have uh, tried Newton's method. Here's what I did. I did Newton's method on Desmos just for ease of time. Uh, After the first iteration, your new x guess becomes 1.5. So your initial guess was 1. Your next guess becomes 1.5. When you do Newton's method again, which is x minus the function value divided by the derivative, you get 1.347. Then you do 1.347821. Remember, if you're using a calculator for something like this, you have to store the value. You cannot round prematurely on the AP test. So the next value becomes 1.3252004. The next value becomes 1.3247. We might think we're done, so we take a look at 1.3252004 and subtract it from 1.3247182, and we end up with 0.0005 and then some additional stuff. So that's not less than 0.0001, which is what we needed. So we have to do one more iteration, and then we end up with something that is 1.3247180. And if we did that subtraction, that would be less than 0.0001. So the rounded to 3 decimal place answer, or actually rounded to 4 decimal place answer because it says 0.001, would be 1.3247. So 1.3247 is approximately the x value where we hit 0. Okay. Um, Finally, a word of caution: Newton's method may not converge if you choose a bad starting point or a point too far away from the root. So we already talked about that. If you see a function like the one on the right, sometimes it kind of alternates and never really gets close to a 0. Um, Also, if you're looking for the root on the left of something and you try something that's closer to the root on the right, or if you have 3 or 4 zeros and you try to find 1 0, you might actually get the wrong 0 if you make a bad guess.